Example 1 is considering 3 functions and is asking us to answer 4 questions for each of the functions. We're going to start with figure 1. First, we have to decide what is the domain of the function in figure 1. If you notice, the function, as it gets really close to 0 from the right, the y values are going towards negative infinity. And as x gets really close to e, the y values are going towards 2. Now, at 2, we have an open circle. That means that the domain of the function doesn't include e. Also, the y-axis becomes a vertical asymptote because I do see that the graph is going towards negative infinity. So then that means that 0 will not be part of the domain. If you notice, there is no graph on the left, so then that means that negative values are also not in the domain of the function. So based on that, we are going to say that the domain of f will consist of everything from 0 towards e, but not including e. For this function right here, again, we see that there is no graph when x is negative. Everything begins when x is 0. The graph goes all the way from 0. It approaches 2. We seem to have an open circle here. However, if you continue upwards, you see that there is a closed dot. So all of a sudden, 2 is in the domain of the function. And then the graph continues all the way down until 6, and then it stops there. So this is telling us that the domain of the function consists of all x values starting with 0 and including 0 all the way to 6 and including 6. For the third function right here, if you notice, now we do have a few negative values up to negative 2. We go all the way down. We have an open circle here, meaning a removable discontinuity. However, when x is equal to 0, even though there is an open circle, we still have a closed dot right above. So then this is telling us that 0 is part of the domain. And then the x values continue all the way to 2. So then we're going to say here that the domain of f consists of all x values between negative 2 and 2, including negative 2 and 2, so including the endpoints. The second part of the question is asking us now to determine where the function is continuous. So going back to figure number 1, if you notice, this particular function is continuous everywhere in its domain, obviously except at e because we have a removable discontinuity, and at 0 because of the infinite discontinuity exhibited there. Therefore, we're going to say that we have continuity in the interval from 0 all the way to e. Again, 0 to e is the domain of the function. In this other figure right here, we see continuity at 0, right-hand continuity, and then all the way up to 2. However, at x equals 2, if you notice, there is a jump discontinuity. So then that means that the function is not continuous at 2. And then the function is perfectly smooth thereafter, stopping at x equals 6. So then we're going to say that we have continuity in the interval from 0 all the way to 2, union, and then 2 all the way to 6. Then when we go over to the third figure right here, we see continuity from negative 2, and then when we approach 0, we have a removable discontinuity there. So 0 will not be part of the interval. And then we have continuity all the way to 2. So then we are going to say over here that the function is continuous in the interval from negative 2 to 0, not including 0, and then 0 to 2. In part C, they're asking us to identify the absolute maximum value and the absolute minimum value if they exist at all in each of the functions. when we go to the first figure right here, we see that in terms of maximum, the y values are increasing as x approaches e. But as x approaches e, we never really reach to y equals 2, what really should be the maximum, because of this removable, this point that has been removed here. Then we practically have to say that we never really reach a highest value. Even if we claim that there is one, that this is the highest value, because this open circle is here, we can always argue that there's one that is even bigger and bigger and bigger, but we never really reach 2. So there is no absolute maximum value. In the other direction, the graph really approaches the y-axis asymptotically. So then these y values are getting smaller and smaller and smaller and smaller. But because they tend to negative infinity, there is never a minimum value that is achieved. So in this graph, we are going to have to say that there are no absolute extrema. So no absolute extrema. Please remember that extrema, saying extrema, that means, or absolute extrema, it means that there are no absolute minimum or no absolute maximum values. That's what this says. No absolute max and also no absolute minimum. Now, going on to figure 2. So in this case, let's see what happens. It seems as if indeed we do achieve a highest y value. In this case, we have a heavy dot. So indeed, there is an absolute maximum, and that happens precisely at x equals 2. And then when I go down on this linear part, we do achieve a lowest y value of -2. So here, yes, here we have an absolute maximum and we have an absolute minimum. So then we are going to say that the absolute maximum value happens to be 6, and it happens at x equals 2. And then the absolute minimum value is -2, and it happens at x equals 6. Then going on to figure 3 right here, the highest y value that is achieved by this graph happens to be 3. And in both cases, we have heavy dots, so 3 is part of the range of the function. Now, the lowest y value should have been 1, but unfortunately there we have an open circle. Then that means that again, we never reach 1. The y values, they get really, really close to 1, but we can never get there because this point right here has been removed from the graph. So then in this case, we are going to say that there is an absolute maximum. The absolute maximum value happens to be 3, and it happens when x is equal to plus or minus 2. But then there is no absolute minimum. The last part is asking us to identify any local extreme values. That really means to figure out if there are any local max or any local minimums. Now, when we find this local max or min, we will also specify the values of x where they occur. All right, I think that the easiest way to tackle this question is by remembering Fermat's theorem. If you remember, the theorem said that if a function has a local maximum or a local minimum at a particular value of x, then that value of x is a critical point of the function. It's a critical point. In other words, at this value of x, the derivative is equal to 0 or it is undefined. Now, to be a critical point, that means that this point has to be in the domain of the function. So we are going to be avoiding any values of x that are not part of the domain that we already specified here, here, and here. Again, format said that if a function has a local max or a local min at a value of x, then x must be a critical point. So I am going to be looking for places where the derivative is equal to 0 or where the derivative is undefined. When I look at this figure right here, I don't see any mountains or valleys indicating that my derivative is 0, and I don't have any sharp corners or places where the derivative is undefined. Now, if you're thinking about the endpoints, the function not being differentiable there, in pretty much all of these discussions, we avoid the endpoints from the point of view of differentiability, because at the endpoints, we can only talk about one-sided derivatives. So we don't want to be talking about a one-sided tangent line, put it that way. Therefore, it is okay, it is common to avoid the endpoints. So we're just going to be looking at what happens in the domain of the function, avoiding the endpoints. So in this case, we will say that there are no local extrema at all. All right, so no mountains or valleys, and no places where the function is completely not differentiable. Now, in this case, figure 2, again, avoiding the endpoints, let's see what is happening. I see a valley right here. So then this is indicating that I have a local minimum. If you notice again, if I consider a small neighborhood around 1, within that small neighborhood right here, 0 is the lowest y value achieved by the graph. So I already see that I have a local minimum. Now, do I have a local maximum? Well, I don't see a mountain, but I do see a place where the function is not differentiable. And then on the right of 2, the y values reach all the way up to 6, 6 being included. And then on the left of 2, in a small neighborhood on the left of 2, I never reach to anything that is bigger than 6. So I claim that 6 is a local maximum. So here I have both. I have a local minimum. The local minimum is going to be 0, and this happens when x is 1, and we have a local maximum. The local maximum is going to be 6, and this happens when x is equal to 2. Then we go to figure number 3. In figure number 3, let's see, again, avoiding the endpoints. We're looking for critical points. And for a critical point, you have to have completely a small open interval around that value of x. So in this case, look at this. I have a place here where my function is not differentiable. The derivative doesn't exist. So if I consider a small interval around it, let's say here and here, going up to my graph in this way, then within this small interval here, 2 happens to be the highest y value. Do I have a smallest y value? I'm hoping that you're noticing that we don't have anything else. We may have liked to say 1, but again, we have an open circle there because the y value at 0 is not 1, it is 2. So we only happen to have a local maximum. We don't have a local minimum. I am not seeing any more mountains or valleys or sharp corners or anything indicating that the derivative is undefined. So then that means that we only have a local maximum, and the local maximum happens to be 2, and we're going to have no local minimum. So writing that down, we have a local maximum. The local maximum is 2. And that happens precisely when x is equal to 0. And there is no local minimum at all.